to change with operational radar data more in the future with upcoming satellites such as NISAR, SWAT, SAOCOM, and biomass. To change with operational SAR signal scattering over inundated regions. Here I will briefly review the radar backscattering mechanisms in general, with an emphasis on the ones that are primarily relevant to flooded vegetation and open water, shown in red boxes in this figure. So this figure illustrates the different backscattering mechanisms, starting with the one on the far left, which is specular scattering, which occurs when there is a smooth surface, such as a calm water surface, and the signal scatters away from the satellite. This results in open water appearing as dark in the image. The next one is rough scattering, which results when there is slight roughness on the surface, causing the signal to scatter in different directions, but mostly away from the satellite. An example of this would be a water surface that has some level of roughness caused by either short floating vegetation, wind, or heavy rain. Such an area could appear dark, but not as dark as a water surface that is completely smooth. As the surface gets rougher, as shown in the next figure, the larger the signal scattered back to the satellite, and the brighter that pixel will appear on the image. The next signal interaction is volume scattering, which occurs when the signal is scattered multiple times and in multiple directions within a volume or medium. In the case of vegetation, the signal can scatter from multiple components, such as branches, stems, leaves, trunks, or soil. The final backscatter mechanism is called double bounce, which is the one on the far right. And it results when two smooth surfaces create a right angle that deflect the incoming radar signal off both surfaces, causing most of the energy to be seen in flooded vegetation because of the interaction between the smooth water surface structure of the vegetation, such as the trunks. Double bounce is also characteristic of urban areas because, again, we have a smooth surface, which is, say, for example, a road, and then we have vertical structures such as buildings. So you have a backscattering mechanism, and it shows SAR signal scattering over inundated regions. And this figure is an L-band HH polarized image from the Japanese pulsar sensor on board the ALO satellite over an area near Manaus, Brazil. It is a great example showing flooded vegetation as well as open water. The river running through the middle is dark because open water is a smooth surface and causes specular scattering. The very bright white areas throughout the image are flooded vegetation. And what is really impressive is that in some areas, even though you cannot see specular scattering from the river because it is either too small or it is covered by vegetation, however, you can still see the river's extent through flooded vegetation because the signal is penetrating through the canopy and double bounce is occurring. This level of detail on flooded vegetation is truly unique to radar. So let's start out by discussing the SAR signal response to flooded vegetation as a function of wavelength. Generally, the longer the wavelength, the higher the capability of the SAR signal to penetrate through the vegetation canopy all the way to the surface. The table on the right lists commonly used bands in radar and their wavelength range. So SARs operating at X-band are generally operating at a wavelength of around 3 centimeters, at C-band at a wavelength of around 5 centimeters, and at L-band at a wavelength of around 23 to 24 centimeters. As you can notice, this range is quite wide. Numerous studies have concluded that L-band is suited to detect inundation beneath a forested canopy and should be the preferred wavelength for this purpose. However, that capability of L-band and also of other bands to penetrate some forested areas can be reduced or are even non-existent depending on the gaps in the canopy, or especially on the vegetation density. As an example, a couple of years ago, we were conducting some wetland studies in the Peruvian Amazon, and we overflew UAV SAR, which is a JPL L-band airborne sensor, over our site of interest, while at the same time, we had someone on the ground collecting site data. This person was in water up to. In comparison to L-band, the ability of shorter wavelengths like C-band or X-band to penetrate the vegetation canopy is reduced. Also, the penetration of C-band is limited in comparison to L-band. Studies have shown an increase in C-band backscatter for flooded vegetation during leaf-on conditions, and especially during leaf-off conditions, because you have more gaps in the canopy. So C-band generally is more useful at the initial growth stages and if the density of the vegetation is low. Also, C-band data is more sensitive for detecting paddy rice cultivation and herbaceous wetlands. X-band sensors, so for example Terrasar X, in general have even more limited penetration through dense vegetation as a result of high interference with leaves, where backscatter is dominated by volume scattering. However, there have been some studies that have shown the potential of X-band to identify a flooded vegetation for sparse vegetation or during leaf-off conditions. In this case, the transmittivity of the signal through the canopy is increased due to gaps in the canopy of very low biomass areas and the contribution of double bounds dominating the volume scattering. Some other studies have demonstrated the ability of X-band to map flooded vegetation in flooded marshlands and in olive groves. So in summary, L-band is better suited for dense vegetation, but shorter wavelengths might give you reasonable results, especially if there are many gaps in the vegetation. The shorter the wavelength, or the shorter wavelengths are better suited for lower vegetation in general. This is an example of signal penetration through vegetation to detect flooding. Here we have multi-frequency images at C, L, and P bands obtained from JPL's multi-frequency airborne radar called AirSAR. The area imaged is a wetland in the Manu National Park in Peru, and this is an image from 1993. Now remember that C-band has a wavelength of around 5 centimeters, L-band around 24 centimeters, and P-band around 40 centimeters. As you would expect, the longer the wavelength, the deeper the penetration through the canopy, and the better you can detect flooded vegetation. So you can clearly see here the bright areas where there is flooding. And note all of the white areas in the P-band image that are either not present or less bright and extensive in the L-band image or the C-band image. In fact, if you take a look at the C-band image, there's hardly any flooded vegetation being picked up. As you know from previous material, backscatter is dependent on two surface parameters, which are structure and dielectric. There are three parameters related to structure: size relative to wavelength, orientation, and density. In radar, the length of the wave or the wavelength will determine its interaction with surface objects. Size relative to wavelength defines the surface roughness. So if wind ripples on the surface of the water are relative to the wavelength, then the surface will appear rough. Remember that the darker the pixel, the smoother the surface in relation to the wavelength. As the surface roughness increases, the backscatter intensity will increase. In the case of open water, as the surface roughness increases, the brighter the pixel. Orientation influences the interaction of the waves that are either horizontally or vertically polarized. Double bounce, which is characteristic of flooded vegetation, occurs when there are two smooth surfaces creating right angles, such as a water surface and a trunk, resulting in most of the radar signal scattering back to the satellite and appearing very, very bright. If the orientation of the trunks are not perpendicular to the water surface, then double bounce will not occur. I will discuss this further along. Finally, the density of the scatterers and the biomass in the case of flooded vegetation will also influence the double bounce signal return. The greater the biomass, the less penetration through the canopy. This is also a function of wavelength, of course. And the greater the density of scatterers, the less the penetration. If there are gaps in the vegetation canopy, there is a larger likelihood for the signal to penetrate all the way through to the surface. Polarization refers to the plane of propagation of the electric field of the signal, which can be in the horizontal plane or in the vertical plane. Irrespective of wavelength, radar signals can be transmitted and or received in different modes of polarization. There can be four combinations of both transmit and receive polarizations, which are HH, horizontally transmitted, horizontally received, VV, vertically transmitted, vertically received, HV, horizontally transmitted, vertically received, and VH, vertically transmitted and horizontally received. Penetration depth is influenced by polarization. In forests, HH tends to penetrate deeper into the canopy because it tends to be less attenuated than VV. HV is more sensitive to volume scattering and hence is a good indicator of vegetation cover and irrespective of wavelength, radar signals. This is an example of multipolarization images from ALO's pulsar over a part of the Pacaya Sumerian Natural Reserve in Peru, which is a vast wetland ecosystem. The images are at L-band and at HH, HV, and VV polarizations. The very bright areas is where double bounce dominates, and this is where there is inundated vegetation. The very dark areas are open water, and you can clearly see a river through the middle of the image, as well as some open water bodies north and south of the river. Note the difference in backscatter magnitude between the different polarizations. If you focus on inundated vegetation or the areas that are very bright, HH polarization is way more useful for distinguishing flooded from non-flooded vegetation. VV shows flooded vegetation to a lesser extent and even lesser by HV polarization. In general, HH polarization penetrates deeper into the vegetation canopy than VV, and when striking the water surface is more strongly reflected in comparison to VV polarization. HV is more sensitive to volume scattering because of its depolarizing characteristics. Here you can see an RGB image of the different polarizations, HH, HV, and VV. False color images are an ideal way to visualize the information content of the different polarizations through color combinations because you can see the information content unique to each polarization or for combinations of polarizations. So in this case, this is a false color composite of the same three images that you saw in the previous slide. HH is in the red channel, HV is in the green channel, and VV is in the blue channel. The pink areas that are popping out are those areas where flooded vegetation is present. This example shows a pulsar image for an area near Manaus, Brazil, at three polarizations, HH, HV, and VV. Note the backscatter intensity of the river that goes through the middle of the image. Open water is a smooth surface which causes specular reflection, resulting in the radar signal being scattered away from the satellite and appearing very dark in the image. Here you can see that open water is much darker at HV than at HH or VV, and hence easier to differentiate. The reason for this is that since water is a smooth surface scatterer, there is no depolarization of the signal. So remember, the signal tends to be depolarized whenever it scatters multiple times. So for example, when you have vegetation, the signal scatters multiple times from the branches, the stems, the trunks, the leaves, the soil. Note the backscatter intensity. And that's called volume scattering. So depolarization normally occurs whenever you have volume scattering, but not when you have specular scattering. So this is a subset of the same pulsar image shown in the previous slide. It is zoomed over an area where you can see roughness on the surface of the water of the main channel, and hence, which is most likely caused by windy conditions. Notice that as you move east and up the tributary, there is smooth water. There's a transition where that water goes from rough, it's a bit higher backscatter to very low backscatter. That means the characteristics of that water have changed from rough to smooth and more of a specular reflector. And so that's the reason that there's a decrease in backscatter in both the HH and VV polarizations. So the utility of SAR data for detecting flooded vegetation is influenced significantly by the incidence angle. Incidence angle is the angle between the direction of the incident wave and the Earth's surface plane. In radar, the incidence angle increases across the swath from the near to the far range. The area closest to the satellite is the near range, and you will find smaller incidence angles than the area furthest from the satellite or the canopy and reaching the water surface underneath. Large incidence angles will be more sensitive near range, and you will find and this is an example of the effect of incidence angle variation. On the left is a Sentinel-1 VV image, and on the right is the incidence angle variation for the same image. So you can see that it goes from 30 to 45 degrees. The radar is right-looking. Note that as we move across the swath from the near to the far range, the image becomes increasingly darker in tone, around a 3 to 5 dB difference in backscatter. If you measure, for example, the same forest at different incidence angles, then the measured backscatter will be different, even if there has been no physical change in the forest. Every surface feature will have a backscatter that is a function of incidence angle. So you need to be careful when comparing backscatter of a feature when there is a large variation in incidence angle. Incidence angle can especially affect the appearance of smooth surface or smooth targets on the image, such as open water. Smooth surfaces can appear brighter than rough surfaces at small incidence angles, and that's usually less than 20 to 25 degrees. Now let's discuss a source of confusion that might lead to errors when classifying open water. This is a pulsar image near Manaus, Brazil, at HH, HV, and VV polarizations. You can see that the water is dark, but north of the river there are areas that either have no vegetation or very low vegetation, and these areas are easily confused with open water. One way to try to clear this up is using image ratios such as HH over HV. Another source of confusion that might lead to errors when classifying flooded vegetation are urban areas. This is a pulsar image near Manaus, Here we have a pulsar image containing the city of Manaus in Brazil, and you can see that the water is dark. It clearly shows flooded vegetation, which are the very bright areas around the river. On the top, labeled in red, is the city of Manaus.